Good morning or good afternoon. My name is Fátima Montserrat Castañeda de la Hoya, and in this poster I'm presenting a work named as the study of the water content of cadmium oxide to cadmium titanate crystalline grain distribution in thin films obtained by salt gel and their effect on the morphological, optical, and photocatalytic properties. As abstract of this work, cadmium oxide plus cadmium titanate multi-component oxide thin films were obtained by mixing the cadmium oxide and titanium dioxide salt gel precursor solutions, keeping titanium cadmium rate constant as 0.65. Titanium dioxide solution water content was varied from 0 to 5 mol. For each titanium mole represented as an X in steps of 1 mole to evaluate its effect on the properties of cadmium oxide plus cadmium titanate films. The films were obtained by the deep coating method under controlled temperature and relative humidity conditions. Superficial morphology images by optical and scanning electron microscopy reveal a strong effect of the water content of the cadmium oxide and cadmium titanate crystalline grains distribution, showing 3 different zones. This result was remarked from X-ray diffraction, EDS measurements, UVBs, and Raman spectroscopy. In addition, the photocatalytic activity of cadmium oxide and cadmium titanate films was evaluated from the methylene blue in water photobleaching. For the first time, a notable effect of the distribution and content of cadmium oxide and cadmium titanate crystalline grains on the photocatalytic activity of the films is reported. The best photocatalytic activity is obtained for the films obtained with X equals to 4 mol, corresponding to those with crystalline grain distribution mass homogeneous. Also, for these films, the highest cadmium excess content to titanium is found, so the highest photocatalytic activity is explained by the higher amount of cadmium oxide and cadmium titanate crystalline grains coupled. In this section of experimental details, as I said before, there were made 6 different precursor solutions with titanium cadmium rate maintained constant at 0.65. These 6 precursor solutions, the content of water of these 6 precursor solutions was varied from 0 to 5 mol of water per titanium mole. And the final precursor solutions were kept at 4 degrees Celsius after obtained. The films were deposited from these precursor solutions once these reached room temperature on glass substrate by deep coating at 3 centimeters per minute with draggle speed. The deposition was made under controlled relative humidity and temperature, introducing ice inside the depositing chamber. The films were constituted of 5 coats, and after each one, drying and sintering treatments, were made at 100 and 490 degrees Celsius, respectively, using a muffle in an open atmosphere. Thin films were characterized by different techniques. Morphological, optical, structural, and photocatalytic properties were determined. For photocatalytic characterization, it was evaluated from methylene blue photobleaching in aqueous phase. Quartz cells were filled with 3 milliliters of methylene blue solution at an initial and fixed concentration, as we can see in the image. Inside the quartz cells, the photocatalytic films were collocated. This arrangement, quartz cells with the methylene blue solution and the photocatalytic film were placed inside a cylindrical reactor, which along its axial axis has a hermicidal lamp. The different arrangement for each film, for each X value, was irradiated during a range time from 1 to 5 hours, and after 1 hour of experiment, one of these arrangements was removed. This for each one of the films prepared. Immediately after that, methylene blue absorbance spectra were obtained by a spectrophotometer. The residual methylene blue concentration was determined from the integrated area of each spectrum, calculated in the 400 to 800 nanometer range and following Beer-Lambert's law. In the image below photocatalytic characterization, I show you a typical degradation experiment of methylene blue solution and its corresponding absorbance spectra. As a result of this work, I'm going to show you briefly what we got from the morphological properties. First, we can see in figure 1 the surface morphology of the thin film deposit, the different water molar contents in the final precursor solution. We can see 6 images corresponding to each one of the different films prepared with the different 6 precursor solutions prepared. Something that we can observe in this image is that a characteristic that all the films share. The films are constituted by 3 different zones. One of these zones is the segregated grains on the surface, what we label as zone C1 or C1 zone versus. And we can see that these grains on the surface, they tend to aggregate in a kind of island. And this island is what we call or we label as Z2 zone. Also, we can see in the film a smoother zone where there is no presence of any grains, and this zone was labeled like a Z3 zone. Also, something important that we can see in this figure is the morphology change after we change the water molar content from 2 mol to 3 mol in on. We can see a larger number of grains segregated on the surface, and of course we can see that the distribution is more homogeneous, being the most homogeneous distribution for the 4M film. These images were obtained by an optical microscope, and the films were analyzed for scanning electron microscopy. In figure 2, I show you the surface and cross-section images of the 2M film in these 3 different zones. In the first image, in the main image, we can see the surface of the film. We can see the presence of these 3 different zones, and making a zoom of each one of these 3 zones, we can see that these grains has a triangular shape, and for the case of this thin film, these grains are big, really big. We can see 2 for the C2 and C3 zones. Some roughness in the fields, being the Z3 zone a little smoother. The thickness of the films were analyzed also, but by scanning electron microscopy. We can see in the images that for the Z1 zone, we have a larger thickness in comparison with zones like Z2 and C3, being the Z3 zone, the one with the less thickness. In the case of the 4M film, with the film with 4 moles of water, I show you in the figure 3 the corresponding surface images by SEM2 in these 3 different zones. We can see in this case, in the main image, the presence of these grains on the surface, but we can see that these grains are smaller than for the 2M film, as I showed you before. And we can see too that the distribution of these grains is the most homogeneous in comparison with all the films. In the right side, we can see a zoom for each one of these 3 zones. We can see for this Z1 zone that it maintains its triangular shape, but we have the size of the grain is shorter in comparison with the 2M film. We can see too that for the Z2 and C3 zones, we have some kind of roughness in the surface, and we can see that the Z3 zone is a little bit smoother. For the structural properties, in the figure 4, I show you the results obtained by the X-ray diffraction. In this figure, I show you the XRD patterns of the cadmium oxide plus cadmium titanate films with different water molar content in precursor solution. We can see from this figure that our films for all the water molar concentrations present 2 phases. Our films have polycrystalline quality. They have the presence of cadmium oxide and cadmium titanate only as only phases in the film. We can see from the intensity signals between the 2 phases that cadmium oxide is more present, or is present in more quantity in comparison with cadmium titanate. And as we can see for the intensity of the signals corresponding to cadmium oxide, we see that the signals corresponding to cadmium titanate are not so visible in the figure. In the part B, we can see that we have the signals corresponding to cadmium titanate. But as I said before, due to the high intensity of the signals of cadmium oxide, we can see the cadmium titanate so present in the main figure. We also, as structural properties, made a analysis of Raman spectroscopy. Let me see. I can move this. We can see in the first image corresponding to 2M thin film that we have we made analysis for the different 3 zones that we observed in the morphological and the results of the morphological properties. We can see in the C1 zone a wide band that extends from 150 to almost 500 centimeters, and this band is centered at 250 centimeters, and in the figure A we can see the convolution of this spectrum, and we can observe 6 different vibrational modes corresponding to cadmium oxide. So we confirm here that these grains segregated on the surface corresponds to cadmium oxide. In the case of the other zones, we can see in the Z2 zone, some vibrational modes corresponding most of them to cadmium titanate. And we can also see a vibrational mode in 142 centimeters, and this corresponds to titanium dioxide in anatase phase. So for this film, for the 2M film, we can say that this zone, the zone C2 corresponds to cadmium titanate. In the case of the Z3 zone, we can observe that when we made the analysis with the red line, we didn't observe clearly the vibrational modes of any of this phase, cadmium oxide or cadmium titanate. However, when we made the analysis with the blue line, a more energetic line, we found the vibrational modes corresponding to cadmium titanate. So this zone corresponds to cadmium titanate. In the case of the film 4M, we found the next. We can see that for the Z1 zone, this wide band that extends from 150 to 500 centimeters, centered in 250 approximately centimeters. So this zone for the 4M film corresponds also to cadmium oxide. In the case of the Z2 zone, we can see the next. We can see some vibrational modes corresponding to cadmium titanate. However, these are overlapped they are overlapped with a wide band that we have seen before, no? In the figure A, we can see that the convolution of the Raman spectra of these zones We can see in the image, in the figure A, we can see the corresponding birational modes of cadmium titanate, of course, but we can also observe these modes corresponding to cadmium oxide. So, in the case of the 4M film, we can see that in the Z2 zone, we have cadmium oxide and plus cadmium titanate in the same zone. For the case of the Z3 zone, we can see the same. We see the same behavior. For the red line, we couldn't see clearly the signals corresponding to any of the phases. However, when we analyze the Z3 zone with a more energetic line, we can see the corresponding birational modes of cadmium titanate. The reason for what we we had to use a more energetic line for this Z3 zone is because, or it's explained by the fact that, as we saw in the morphological properties, this zone has the shorter or thickness in comparison with the other with the Z1 and Z2 zones. So that's the reason we had to use a more energetic line to see clearly the presence of cadmium titanate. One explanation because of the behavior of the difference between the Z2 zone of the 2M film and the other on all the other films in comparison con the Z2 zone of the 4M film is because we can see in this Z2 zone for the film 4M, we can see cadmium oxide and cadmium titanate because we have a more homogeneous distribution of these cadmium oxide grains. So it is expected that this Z2 zone contains or shows more cadmium oxide in comparison with the other films, where we can see very clearly the difference between these three zones. We can see here in the optical images, we can make a difference between the three different zones for most of the films, except for the 4M film, where we can see we have a lot of these grains distributed along of the surface of the film, and we cannot differentiate between these three different zones. We can see the segregated grains, and that's it. So these Raman results could be explained by this, by the morphological distribution of these grains. For the photocatalytic activity in the case, in the figure 6, I show you the reaction constant for all water content in the precursor solution. We can see in this image all the reaction constants for the films prepared, and as I said in the abstract, the film with the most with the with a higher photocatalytic activity was the one prepared with X4 mole of water. And in this case, the result is explained by the fact that for this film we have more numbers. We have a higher number or higher amount of crystalline grains of cadmium oxide coupled with crystalline grains of cadmium titanate. As we can see from the results obtained from from X-ray diffraction, what we got from Raman spectroscopy, and what we observe in the morphological properties, we can see that for this film there's more cadmium oxide grains distributed on the surface, and the distribution is the more homogeneous. So it is expected that we have a bigger area covered with these grains, and there are more available sites where this coupling can be done, when this coupling can carry the photocatalytic reaction. From EDS measurements, I obtained the cadmium excess with respect to titanium, and it was obtained for all water contents in the precursor solution. And this is for the zones C2 and Z3. Because we know that the zone C1 corresponds to mostly cadmium oxide. We can see the most important thing of this figure is corresponding to the thin film with 4 mole of water. We can see that in the Z2 zone, it has the higher cadmium excess, and we can see too that in the Z3 zone we have also for this zone it has the higher cadmium excess in comparison with all the other films for these two zones. So with these results we can prove that this film, the 4M film, has a larger number of cadmium oxide grains distributed on the surface of the thin film, and these cadmium oxide grains are coupled with cadmium titanate. And as conclusion of this work, briefly, the water content in the precursor solution and the closest space to the film immediately after its removal from the precursor solution has a crucial effect on the cadmium oxide to cadmium titanate crystalline grain distribution, impacting their properties. The best homogeneous distribution of cadmium oxide crystals on the cadmium titanate film surface is obtained for X equal to 4 mole of water, where the cadmium oxide crystalline grain's highest content is exhibited. Furthermore, the highest photodegradation of methylene blue obtained for X equal to 4 mole is associated with the best coupling among cadmium oxide and cadmium titanate crystalline grains. Finally, all techniques of characterization used were fundamental to conclude these results. Thank you for your attention, and if you have any doubts or questions, I'll be presenting this poster in the corresponding section and the date marked. Thank you.